Okay, and we'll move on to our third speaker, Mastroserio, and his talk is entitled Modeling X-ray Time Lags in Stellar Mass Black Holes.
Can you hear me, John?
Yep, we can hear you and your slides are up.
Okay, perfect. Well, thank you very much, and good afternoon, everybody. I'm Guglielmo, and I work at Caltech with Javier Garcia and Riley Connors. And today I'm gonna present a model that tries to fit for time lags in accreting black holes. I developed this model with Adam Ingram, and we are still developing this model with many collaborators. You heard a lot about reflection and the corona. Of course, wherever you want to put the corona, on top of the disk as a lamppost, on top of the black hole as a lamppost, or a more extended corona like a hot flows and a truncated disk, we still need to address the reflection and the lags that come with the reflection. So from a timing point of view, we see variabilities from the corona, and this variability is transferred to the reflection. But because of the different light crossing time between the reflection and the direct emission, we should see some lag between these two components and between the two variabilities. So what's the best way to detect this? Well, we can take the easiest, which is considering two light curves in two different energy bands. Here, the first one is a soft energy band where the reflection dominates. And then the hard energy band is where the direct emission dominates. If we compare these two light curves and variability, we can get the lag. And this is something that has been done a lot in supermassive black holes, but also in stellar mass black holes. And recently, we discovered also in stellar mass, people discovered in stellar mass black holes that we have soft lags at high frequencies. This means that the soft light curve is lagging behind the hard light curves. So what we expect from the reflection. But we have seen for many, many years also another type of lags, hard lags at low Fourier frequencies. So here, I want to mention something that when we talk about soft lags associated to reverberation or reflection lags, we should be careful, because I want to show you just one example where I produced a spectrum with like a reflection model, just changing the ionization. And you see how now in the bottom panel, in the soft light curves, the reflection doesn't dominate anymore. So if we do the same analysis in this situation, we shouldn't find any lag. So my message here is that probably soft lags is associated to reflection lags. But when we look at the evolution of the lag, then we should be careful on saying something about the geometry of the system, because we have to take into account the fact that also these two components can change, and also changing a parameter like the ionization can change these soft lags. So what's the best practice then is to look at everything, not only at the lag as a function of frequency, but also at the lag as a function of energy in different frequencies. And what people have found is that in the lag energy at low frequencies, we see a lag spectrum, I like it to call, pretty much featureless. While in the at high frequencies, we have a very different lag spectrum that has some feature like a lag at low energies, and something that resembles an iron line around 6.4 keV. So this iron line is actually what tells us probably that this comes from these high frequency lags come from the reflection. And I want to mention that, of course, we analyzed some great nicer data, but probably the first detection was by Barbara DeMarco in 2017 with GX 339-4. And with data that are XMM data. And then, of course, we had the confirmation of this feature with much better, nicer data in MaxiJ in 1820. So what we want to do is to fit this with a proper model, with a model that can constrain this data. So that's the model that we developed. Is a ray tracing model that accounts the impulse response function of the disk. But not only this, it has much more. It considers like a proper disk. So we have a silver model and the characteristics of the disk in the reflection. For example, recently we added high densities to the lag model that we have, and you notice how the picture of the lag spectrum changes quite significantly when you consider high densities in the disk. Now the lag at low energies pops up quite nicely. So I give you just a teaser that here is not a fit, but just like overimposition of model and the data. And you see how our model does a good job to reproduce the shape of the data. So we were encouraged to fit this data set. Again, this is MaxiJane 1820. But what we want to do is not just stop at the lag due to the reflection, but also all the lags. So also the low energy, the low frequency lags that we see that probably is due to the continuum emission. So how do we fit also that lag self-consistently? Well, people usually have addressed these hard lags with mass accretion rate fluctuations propagating through the disk. These fluctuations have different variabilities depending on the radius, and they then illuminate the corona. But the picture is a little bit more complicated than this. So on top of these propagating fluctuations, we have also seed photons illuminating the corona. So the corona is changing. And what people have done usually in the past is let the emission of the corona changing just with the normalization. So the variability was produced by changing in the normalization. But because of the complication of the scenario, it's not absurd to think that the variability is actually different, and it's caused also by variations in the hardness of the power law. And here in the sketch, the effects has been hugely amplified. These fluctuations that we account in our model are just tiny fluctuations of hardness and, of course, also normalization. And if you want to know a little bit more about the idea of these fluctuations, where they come from, the illumination of the corona, you can check Phil Atlay's poster in this conference. Well, so
you got about 2 minutes left, okay?
Okay. So we got we have to put all together, and we put so once we pivot the power law, the reflection sees this power law pivoting, and it pivots as well. But what is changing is not only the hardness, but also the ionization level in the reflection. So there are like secondary effects that we need to take into account. And this pivoting of the power law and of the reflection causes their own lags. So we have basically three sources of lags. One is due to just the pivoting of the power law. One is due to the pivoting of the reflection, and then we have light crossing time that we account for with the ray tracing model. So what we did is to fit to the data again, MaxiJane 1820 with nicer, a really good data set, and you have seen Jingyi's talk yesterday where she fit with this model, RelTrans, the whole transition. What I'm going to show you is one single observation, and I'm going to split our fit to show you how the model picks up the different components. So these different type of lags. So we have here the blue line, which is the lag due to the pivoting power law, just the pivoting power law. Then the red line is the light crossing time, pure light crossing time. And the green dotted line is light crossing time plus these effects of the pivoting of the reflection. And you see how the total lag, which is the golden line here, the orange one, is not the sum of these components, because the lag is not a linear operation. We actually sum the cross spectrum of these lags. And you see how in this low frequency observation is the pivoting that dominates. But we have some modification of the lag due to reflection, to the dilution of the reflection at high energies, but mainly the amplitude of the lag is due to the pivoting. Then if we go to higher frequencies, the picture changes completely. Now the light crossing time contributes much more, even at high energies, and at low energies is the only contribution that we have. The big picture is fitting lag energy spectrum for different Fourier frequencies. And here is one fit of one single observation. And you see how going from low frequencies to high frequencies, the different components change and pick up different lags. So for example, the blue is the dominant one at low frequency, and at high frequencies is actually almost negligible, and it's only the light crossing time that fits the data. So I'm going to leave you with my conclusions, saying that I think this is a model that we want to fit this model with on like many sources now to see like these different components, if you can reproduce the data. We did it with MaxiGen 1820. Again, Jingis presents our result, and we were able to infer something on the corona. But I encourage you to contact me. The model is going to be public very soon. But again, if you contact me, I'm really happy to send you the model and start using it for other black hole binders. Thank you very much.
Thanks, Gulo. Let's see, are there questions?
Yes, question in the room.
Okay, we'll go to the room first.
Thank you, Will. Thanks for a very nice talk. I just have a question about the size of the lamppost you require, because in order to have enough seed photons intercepted by the lamppost, especially if it's low height, you need a probably quite large one, as pointed out in a paper by, I think, Chris Don and someone else. I forgot at that time.
Yeah, so as you pointed out, we assume a lamppost because it's an easier way to compute the ray tracing and do it everything self-consistently. But we don't explore that. We know that there is variability in the corona, and of course the corona is not a lamppost. We all know this. It has some extension because it needs to see the seed photons. So this assumption of the lamppost is a good assumption if the corona is compact enough. If it's not, yeah, it's not a good assumption. So this is what we have done. In the conclusion slide, I put that we are working to expand this. We are now trying to simulate the model with 2 lampposts, meaning that a vertical extension. But again, computing the ray tracing self-consistently and doing everything self-consistently with an extended corona is not that easy. So. But this is what we want to do, of course.
Okay, let's go to a question from Phil Utley.
Yeah, hi, thanks. So looking at your fits, when you look at low frequencies in MaxiGen 1820, you're fitting a regime where previously we've seen these lags that we claim are the disk leading the power law emission, right? And you have to have that in your model anyway to get the pivoting, or at least if it's done in the way that we talk about in our poster. So I wonder about the low frequency fit, whether you're kind of limited by, maybe there's a problem with the assumption of the density of the disk, that you're basically kind of overfitting the dilution in some sense to kind of produce this sort of bend in the lag versus energy, because you can kind of see the bend there.
But you mean this one?
No, I don't mean the high frequencies. I mean the low frequencies. So you don't have a disk variability, as far as I understand, intrinsically in your model. So you don't have the disk propagation in there at all. But we see that, right? I mean, also in the covariance spectrum at those frequencies and at those energies below 2 keV. So I think there may be some kind of overfitting of a different model component. And I guess the real question is, what density are you assuming for the disk with this? Because for these X-ray binaries, I think there should be a significantly higher density and therefore maybe different reprocessing at low energies anyway.
But I'm not sure I'm understanding correctly here. So in the lag, we don't see any. So this lag is produced by the effect of the pivoting in principle. So you say that here we are dominated by the disk. It might be true, but it might also be true that we don't see the variability there in the disk.
Yeah, but you have a flattening in the data, which you actually explain with the total lag, which is a combination of the light crossing, reflection, dilution, and the pivoting. If you had the pivoting alone, you wouldn't see that. But that inflection is the thing that we've explained previously with this propagation stuff. So either that's wrong, right? Okay, I'm fine to try that. Or maybe there's an issue with the reflection. But anyway, okay, so maybe we should go on Slack to talk about it.
Yeah, let me just say that it's true, but so what this shows is that you don't need that explanation of the disk, that just the dilution due to the reflection is enough to explain that flattening. Maybe it's not true, maybe it's an overfitting, you're right, but this shows you like this simple model can reproduce the data in this way.
Okay, sure. Yeah.
Time for another question there in the room. Yeah.
Okay.
Yeah, it's Barbara De Marco. So going back to Phil's question, I was wondering if you could predict like covariance spectra from your model and see if you can recover them, because I mean you see the sort of this component in the covariance spectra, those frequencies.
Yeah, we can reproduce we can fit for the covariance spectrum. And I think with Maxi, and we did it before in Senior 6.1 with this good data set. I think the model is not quite there. We have some problems. We think is also associated by like some issue with nicer calibration at low energies. It might be what Phil pointed out, that we don't have the variability in the disk or enough variability in the disk. So yeah, that's a work in progress. We're trying to do that, and it's true. This is just the lag. It's half of the picture. We can do better.
All right, thanks, Gulo. Let's thank the speaker again.